Morning to one and all. Now I'm going to introduce our today's speaker. I would like to tell about him first. He has completed his master's thesis on quantum state estimation using conditional generative adversarial networks, CGAN, under the tutelage of Professor Arbasi Sinha at the esteemed Raman Research Institute, RRI. Prior to this, he earned his BS-MS degree from the renowned Indian Institute of Science Education and Research, Pune. At present, he serves as a project manager at Quantum Insider, a Canadian quantum technology startup. He has published 3 research papers in top-rated journals such as Springer, Nature, and IEEE, and have also filed a patent. In addition, he has overseen the product development of 2 projects and have imparted lessons to students and professors at VIT and SRM Chennai. He is extremely passionate about discussing quantum technologies. He is none other than our today's speaker, Mr. Srikutan LS. I would like to invite him to speak about few words about this gathering, sir. Please welcome. You can take over. Sure. You want a speaker mic, sir? This one or speaker mic?
Am I audible? Yeah. Thanks a lot for the warm invite and actually a really wonderful hospitality by Dr. Kalyani and others. So I'm Srikutan. I'm a recent 1-year graduate from IISER Pune. Just to understand, how many of you have heard about IISER Pune here? IISER here? Yeah, so it's actually pretty sad for me to explain IISER because IISERs are essentially IITs which are supposed to do science education, and it was actually founded 15 years back only. They are national funded institutions, just in the level of IITs and other national funded institutions. IISERs are the place where this sort of technologies are emerging, and that is where I think you should also try to collaborate with them more. There are 10 IISERs and there are also IAAC. So starting on quantum computing, how many of you have heard about quantum computing? How many of you have just heard about quantum computing or have seen somewhere here? Okay. I think all of us would have heard about AI/ML. All of you are actually working on AI/ML probably. Generative AI and cloud computing, metaverse, IoT, 5G, all these futuristic technologies. But bigger than that is going to be quantum computing. And why I'm saying this is, whatever computing that we have been doing till this point is going to be completely changed in a decade. So all these technologies, AI, ML, metaverse, 5G, IoT, all these technologies, we need a computer to build all these technologies. So what if we have a better computer? What if we have a better computer? So that is going to change everything. And that is why I'm saying quantum computing is going to be much bigger than all these computings, all these recent trends that we have. So just to have a quick survey, what comes to your mind when you hear the word quantum computing? It can be as simple as confused because we don't know about it, we don't know anything about it, right? Or maybe you would have heard some other phrases which is adjacent with quantum computing. Quantum mechanics is one word that usually comes with quantum computing very frequently. Any other phrases, any other words that comes to your mind when you hear quantum computing? Anybody faster or speed or something? Huh? Pardon me? Physics, yeah, of course. It is based on a different physics. Now let us take a simple poll. Which computer do you think is the fastest? I said we are going to build a new computer called quantum computer, that is quantum computing. Now whatever computer that we have right now, your laptops, your GPUs, they are called classical computer. So which computer do you think is going to be fastest? So everybody agrees on that fact, quantum is going to be faster? Okay, great. Now let us understand fundamentally how a quantum computer or quantum computer is going to be different from whatever we have today. It is going to be fascinating, it is going to be counterintuitive, it might go above your head because it is deeply rooted in quantum mechanics, as most of you know, and very famously quantum mechanics was a field of physics which was recently developed by the pioneers like Schrodinger, Paul Dirac, Einstein was also there. So it was only 100 years old. And when they started to teach this quantum mechanics in universities, usually in colleges there will be a lack of students for taking different subjects. But when they started to teach quantum mechanics, there was a lack of professors because nobody knew quantum mechanics. And famously, Richard Feynman, the famous physicist, said, if you understood quantum mechanics, then you haven't understood anything. Because it is very difficult to comprehend, it is very counterintuitive. So I'll try to explain with whatever knowledge I have, and I hope you will also understand a bit of quantum computing, quantum mechanics, the basics of it. Even if you don't understand, it's fine, you can go back and read a lot on it. It's very interesting, and it is very spooky, counterintuitive, and it of course grab your attention. So we know classical computer works with bits. We call them bits. For today onwards, let us call them classical bits. We used to call them bits. From today onwards, let us call them classical bits because they are using they're in classical computer. These classical bits are essentially voltages. It can be high, it can be low. So high means 1 and low means 0. So, and these classical bits can only be 0 or 1. They can only be 0 or 1. Once it is produced, it is fixed. Once we produce a high voltage, we know from whatever distance it travels, we know it is going to be 0, or we know it is going to be 1. High voltage means 1, right? And if it is low voltage, we know it is going to be 0. How much of a distance it travel, hopefully no resistance and other thing, it is going to be 0 itself, right? Now, that's why I call classical bits. Now let us come to quantum computer. So that was voltage. Now let us come to quantum computing. Let us come to that regime or realm of quantum mechanics. So quantum mechanics doesn't apply. Quantum mechanics has a lot of weird phenomena and weird features and weird laws, but it doesn't apply to the world that we live in. Like you, me, this chair, this laptop and all. Because they're big, or you can say heavy or huge objects. Now if we go to a range where it is, let's say, atoms, electrons, protons, neutrons, photons, all these particles which you can't see, which you can't touch, which of course you can touch them, but which you can't feel, or which you won't be able to understand a lot of it. So this region, let us call it microscopic, or it's actually nano level, it's much lower than that also. We will call this set of particles, we'll call this particular range quantum regime, where the quantum principles, quantum mechanics and everything are obeyed. That's the region where quantum mechanics and everything are obeyed. So when I say a quantum bit or a qubit, you should try to imagine any one of this particle. So one of this particle, any one of this particle is going to behave and is going to act as a bit for us. It's going to act as a quantum bit for us. I hope that's clear. So let us take a simple example of electrons. We all know electrons, right? So can I get a marker? So we all know electrons, right? And electrons essentially resides in energy levels. That I think was +2 physics. They are in different energy levels around the nucleus. This is the nucleus where there is neutron and proton, and electrons essentially are in different energy levels. And usually there will be infinite number of energy levels, starting from 1, n equal to 1. So we call energy level as 1. We number them. First energy level is 1, 2, 3, and such on so forth. And let us now confine the electrons into 2 energy levels, just 2 energy levels. Just 2 energy levels, and let us say this is the lower energy level and this is the higher energy level. So now we know for sure that our electron can only reside in these 2 energy levels. One is lower and one is higher. Now are you getting a feel how classical bit is compared to quantum bit? So for voltages we have lower voltage, higher voltage. In quantum regime or a qubit we have lower energy level, higher energy level. So this is lower and higher. Now this is actually the most easiest part to understand. Now we can create electrons by a lot of different ways. We can have electrons in different atoms also, right? And once we confine in it, just like voltages, once we have produced that voltage, we know that voltage is high all the time. But if we produce this electron or if we produce this atom system, we'll never be able to say which energy level that electron is going to be. So that is where the whole differentiation starts from. Initially with our classical system, once we produce the bit, we know it is going to be 0 for all the time. But once we produce the quantum bit, you can never know will it be higher or lower. Will it be higher or lower? So that is the starting point of everything in quantum mechanics, and we call it quantum nature of a particle. And this is the essential starting mode of unpredictability of a quantum mechanics particle. Now there are different set of techniques where we can measure or where we can find, okay, we don't know, we can't predict it, but we can measure and find where it is. We can measure and find where it is. Just like we have voltmeter, we have different set of measurement techniques to find which energy level it is going to be in. Now let's say we made 1000 identical copies of this same atom. 1000 identical copies of the same atom and same bit. Let's say we have 1000 identical copies of this qubit. Now we measure 1000 times. Each of the atoms we measure 1000 times. What I'm going to say is an example, just an example. What I might see, I'm not saying what I will see, what I might see is that, so lower let's call it 0, higher let's call it 1. What I might see for 300 times is 0 and 700 times is going to be 1. So that is where the probability comes in. That means 0.3 time I'll get 0 and 0.7 time I'll get 1. So this fundamental property is called quantum superposition. Quantum superposition, which is essentially which we actually melt it down and say a quantum bit can exist in both 0 and 1 at the same time, and we call that phenomena quantum superposition. So this is actually in much more depth, because that statement will actually leave a lot of details. You might not understand what is qubits and other things. So essentially what does it mean is that if we measured this 100,000 times and if we get 0,000 times, there is no probability. There is no superposition of different states. This is actually a superimposition of different states. If you remember, there is force. If you need to sum up different forces, right? There is we add all those forces in vector summation and other things. This is similar to that. 0.3 times we'll get 0 plus 0.7 times 1. This is the state of this qubit. So 0.3 times 0 plus 0.7 times 1. This is the state of this qubit. So we can't say the state, we would have said the state of the classical bit is 1 every time, that's just 1. But here it is a summation of different state and with different probabilities. That is, you measure this thing, there is a chance of 0.3 times, there is a probability 30% of times you will get 0. There is a probability 70% of the time you will get 1. So this is the fundamental difference of a classical computer and a quantum computer. And this is just a starting. So this is the starting, and I hope you understood at least a bit of it, at least 50% of it. It is of course going to take a lot of reading to get to know this much more better. And I would like to ask if you have any doubt here. I will be happy to take anything and clear it now itself, because it's very fundamental. I hope this is clear. Okay, great. Now this is just one of the weird phenomena that we have, one of the weirdest phenomena that we have. Then there is another weirder phenomena that we call quantum entanglement. That we call as quantum entanglement. Now, to understand quantum entanglement, I'll try to start with a simple example. Let us say we create two qubits at the same time. Let us say we create 2 qubits at the same time. 2 qubits, and they are here. And we can create qubits in such a way that they are intercorrelated. They are correlated. That means you only want to measure let's say this is qubit 1, this is qubit 2. You only want to measure, so while measuring we will get which state it is in. So that is what I call it measuring. You only want to measure one of the qubit to understand the state of the other qubits. So that is called quantum entanglement, where there is a correlation between 2 different qubits, where you only want to measure one of the qubits to understand the state of the other qubit. Now there is also a lot of depth into this thing. There is a lot of mathematics involved, but it will take a lot of time to actually explain this with the mathematics, so that's why I won't be going into that. So to understand this, there are 2 main phenomena. One is a quantum qubit or a quantum bit can exist in 2 different states, and it can be a combination of all these states, and it can reveal one of its states while we measure it. It reveals one of its states while we measure it. And there can be other weird phenomenon where these 2 qubits are correlated in some way, and you only want to measure one of the qubit to actually understand the state of the other qubit. So these 2 phenomenon And the best part is that these two qubits, right, they don't want to be in the same place. They can be thousands of meters across. This qubit can be in Vishakhapatnam and this qubit can be, let's say, in Hyderabad. Then also, if you measure this qubit, you will be able to see what is the state of the other qubit. So these two phenomena, if we can exploit these two phenomena to make a computer, that is where we will be able to actually crunch in, or we can store a lot of information, huge amount of information in less number of qubits. So I'll give a simple rubric which is not accurate, but a simple rubric for you to understand. If we have 5 qubits, just like this, let's say we have 5 qubits. It can, let's go with 3 qubits then. Let's say we have 3 qubits. It can actually encode 2 raised to 3, that is 8 bits information in it. So for example, what I'm saying is that let's say we have 3 qubits and it can be 0, 1, 1, 1, 1, 0. There are actually 8 combinations here, 2 into 2 into 2. A qubit can code all these 8 combinations in just 3 qubits. If it is qubit, it can code all these 3 combinations in 3 qubits. But what if it was a classical bit? It need actually multiple number of bits to actually encode all these things. It is going to be difficult, right? It's going to be very difficult to encode all these combinations in bits. And this is the power. And that is where a lot of information can be, huge amount of information can be crunched into quantum computer, and we only need a smaller processing power. That is, we only need smaller processors, and also it will be hugely or exponentially faster than other classical computers that we have. So So here, let's say we have 3 qubits, and as we know, these qubits can be in a superposition of 0 and 1, 0 and 1, 0, 1. And due to this, there will be 8 combinations possible, total 8 combinations of 0 and 1, that is 1, 1, 0, 0, 0, 1, and other combinations. Now, because of quantum superposition and entanglement, a qubit, these 3 qubits can encode all these states. That is 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1, 0, 0, 0, and all the 8 combinations. Just 3 qubits can encode all these 8 possibilities. 3 qubits. But if you need to encode all these possibilities in a classical bit, it is going to take much more number of bits. It's going to take much more number of bits, not just 3. It's going to take actually more than 8. And that is where we'll be able to crunch in a lot of information into qubits, lesser number of qubits than the classical bits. And this is where the immense computing power comes in, and also faster computing. And so I hope these two fundamentals are clear. Then I think going forward it will be actually easy. There won't be much difficulties. It will be just like another computing that you're going to learn. So here you can see I've written qubit as A1 plus B0. So this is essentially 1 is the state 1. It's a fancy way of representation. We call it bracket notation or Dirac notation, which is a fancy way of representing the state 1. And A is essentially the probability. A is essentially the probability of that particular state. Now this is the main reason, this are the two main reasons where and why quantum computers are going to be much more faster and powerful than classical computer. So to give an example in a practical sense, it is also not accurate, very accurate in terms of how I'm going to explain. There is many other practical implications and practical problems in devising this sort of hardware. But anyway, just to get an understanding, let's say we have a maze, and to come out of the maze, there are 1,000 ways of coming out of the maze. There are 1,000 possibilities of actually going. There is no, you can go here. There are 1,000 possibilities, and only one of the 1,000 possibilities is the answer, is the correct answer. Now, due to quantum superposition and entanglement, a quantum computer can essentially go through all of these 1,000 possibilities parallelly or at the same time. Now, a classical computer, what will do? It will go sequentially. It will go path A, path B, path C, path D, and it will take a lot of time. But a quantum computer can essentially go through all of these possibilities at a time, at one go, or you can say parallelly. There are making such a quantum computer, but this is theoretically how it is going to work. So it can essentially go through all the 1,000 possibilities in a go, rather than a classical computer where they want to go through all these sequentially, after path A, path B, next path C, path D, and other paths. So this is how the power of quantum computer will come in act. Now coming to the question, actually quantum computers are not fast. We can't say faster. For a simple application like multiplication, let's say this numbers P and Q are 248 bit numbers, integers. Classical computer will take a very fraction of times. It is going to only take a fraction of a minute. But quantum computer will take 75 seconds. So we can't say quantum computer is going to be faster for all the tasks that we have. We can't say quantum computer is going to be faster for all the tasks we have. It is not going to be, but it is going to be exponentially faster. You can't even imagine how much fast it is going to be for applications like factorization. So factorization is essentially the reverse of multiplication. You want to find which two numbers gave you that particular number n. Now if we need to find, let's say, P and Q, especially prime factorization, it's a very difficult problem. People who are working in cryptography might know prime factorization is one of the cornerstone of all the algorithms that we use. So most of the cryptographic algorithms that we use, RSA and other elliptical cryptography and other algorithms. Now, to do prime factorization, which is one of the most difficult computational tasks, it will take 4.7 billion years for a 2048-bit integer. That's why all our systems and all the information technology it's available in internet is secure for now. That's why it is secure for now, because nobody is going to crack the RSA or other classical systems that we have, classical security systems that we have. But for a quantum computer, it is going to only take 8 hours. So that is where the power comes in. For this sort of problem statements where there is an immense or exponential amount of search space, because essentially what quantum computer does is searching through all these numbers and finding the best number out of it. So immense amount of search space is there. It is going to be able to it is going to fast up all these computations, and it is going to change a lot of things that we know of now, because this is one of the examples. Factorization is the key thing in cryptography that is going to change. Once the quantum computer is coming, that will definitely change. And it is already started. It has already started. For people who are interested, you can check these two things in terms of security. Post quantum cryptography, or PQC, and then there is another thing called quantum key distribution, or QKD. So these are two different areas for people who are interested in security to check out. Very interesting things, and very interesting areas where a lot of developments are going. Just to give another example of how the computing power is going to change. Earlier we spoke about how speed is going to change. Here how computing power is going to change. Penicillin, as you know, it is being a lifesaver for the humanity. And it was accidentally discovered. And there would have been no way for us to actually manually discover it, because the amount of bits that we need to simulate to identify a molecule like this. Essentially what happens in molecular or pharmaceutical companies are, they try to bring up all these different sort of molecules, different atoms, other things to find or generate different new drugs. And then they will simulate their reaction with different sort of bacteria and algae, different sort of microbes, to identify how it is going to perform. So if they would have want to perform this task on penicillin, it would have taken them 10 raised to 86 bits. I think it is larger than the number of atoms in the universe. And for a quantum computer, it will only take 286 qubits. And this is the example of how computing power how much computing power we can reduce, and we'll be able to solve huge amount of we'll be able to solve bigger problems for humanity, like solving cancer and finding better drugs, finding better EV materials, finding better battery materials, better materials in general, because molecular simulation is a huge part of the drug industry, the EV industry, the automotive industry, and other things. To sum it up, classical computers will remain as it is. Tomorrow, or let's say a decade from now, you won't be sitting here with a quantum computer, quantum powered laptop. So that is not going to change. You'll still have classical powered laptop that you use today, and you'll use that for multiplication, where quantum will be used for factorization, much more difficult task. And where you will use classical computers for visualization, to view the molecules, to view other different type of things. But you'll use quantum computer for simulations, where you'll get the results in your in your classical systems, where there will be a quantum computer backing it up to actually simulate it and show you that results. And we'll use it for video conferencing and other normal stuff that you use. But quantum computers will be used for optimization, machine learning, different sort of chemistry formulations, and other material discoveries. So this is the applications in a real life, and this is the chart where you can understand where to start using quantum computer. So I have been talking about classical computer and quantum computer, and it is going to change, how it is going to change the world. But for most of the things that we have right now, for most of the problems that we have right now, we might not require a quantum computer. We might not require a quantum computer. This is a good example of where to look for. For example, let us take drug discovery. Let us say we only have a small molecule. Let's say only 3 or 4 atoms. You don't need a quantum computer. Medium sized molecule, 10 atoms, you don't need a quantum computer. But it's much more bigger molecule with high accuracy. This is where in drug discovery the things come. Even if it is 10 atoms, if you need high accuracy, you will require quantum computer, because right now what classical computers are doing is essentially approximation. They have different numerical approximation, a lot of different numerical techniques to approximate, but it won't give you the right result. It won't give you the accurate result. Only a quantum computer can actually find the accurate result for you. And if you want accuracy, and that's where the number of bits goes in. No? If you need, in general for classical computer, 1 million bits, that is where I think you can start looking for a essential application of a quantum computer, where these are other different practical use cases. Delivery planning is the biggest use case that a lot of the companies are exploring right now. City, if you want to do it nationwide, it is currently impossible. Right now also, if you see the delivery optimization is also really in a bad state. You know, you'll say you'll get in 1 day and you'll be getting after 10 days. So that sort of optimization is also in a pretty bad state. Now, we have talked about all these different applications, quantum computing fundamentals and everything, but all of you will be asking, like, I can see my laptop in front of me, that is a classical computer, but where is QC or where is quantum computer? Where do I find it? How do I use it? How can I find and start writing algorithms on it? So this is an older chart. Now again, this is a very interesting chart, because right now I was just saying quantum computer. That was the word I was using. But there are two different types of quantum computers. One is gate-based quantum computers, or we call it universal gate-based quantum computers. So it is essentially how we have classical computers. We have gates, we have qubits, and you add it up to make a quantum circuit and then execute it. Now there is a different type of quantum computer called annealing based quantum computer. It have no comparison for that in classical, so it will be again difficult for me to explain, but essentially it is a different type of quantum computer which is not universal. That means you can't use this type of quantum computers for all the use cases that you have. You can only use it for use case called optimization, where you have a lot of different answers, a lot of different possibilities, and you want to get down to one optimal answer. So that is the main use case. So it can't be used for machine learning and other sort of use cases. So annealing type of quantum computer. Now inside the universal gate based quantum computer, we have different other type of architecture in a sense. For example, we have voltages for all our classical bit computer. Now, all our we model classical bits as voltages. Now, in quantum computer, if you remember, I started with saying neutrons, protons, electrons, atoms, ions, all these quantum particles essentially show quantum phenomena. So we can actually make a quantum computer using any of these quantum particles. So we can make a electron based quantum computer, we can make ion based quantum computer, we can make atom based quantum computer, we can make photon based quantum computer, we can make silicon based quantum computer, carbon nanotube. There is actually 12 different types or 12 different methods with you can make a quantum computer, because all the particles shows this phenomenon and we can make a quantum computer on top of it. And that's where this differentiation comes in. Two types of different quantum computers, and inside universal gate based quantum computer there are different types of architecture, or what do you say, methods of building quantum computer. Now superconducting architecture, this is an architecture which is not actually a quantum particle. They are not an atom, or they are not a quantum particle. They are essentially what we call artificial atoms. They are simply circuits where they are LC circuits, and they are programmed to behave in a way of atoms. So this is the most prominent architecture. It's not an actual quantum particle. They are LC circuits, and they're programmed to behave like an atom. And prominent one, most of the companies build quantum computers on top of superconducting architecture. So, do you know what is this? It looks like a chandelier. Do you know what this is actually? Yeah. So this is a quantum computer. You might not expect a computer to be in this shape, but this is essentially quantum computer. This is the mechanism, or this is the architecture where the chip is held. This is the whole architecture where the chip is being held, and below there will be a small chip, just like we have in CPU now, small chip, and there will be a huge channel or huge cylinder circumferencing this quantum computer to keep it cold. It needs to be, most of the quantum computer need to be in a temperature range of minus 270. Okay, so it's actually near zero temperature. It's 273 degree Kelvin, which is the lowest temperature possible, and that is the range of temperature is required to operate these atoms and operate these quantum computers. And this is the system, and as I've told before, there are multiple types of architectures, that is atom based, ion based, photon based, and for each of these different type of architecture there will be different types of computers, and some of them can work in room temperature, some of them can only work in this 0 degree temperature, near zero temperature. Now let us see how we can actually compute it, or how we can program it. All these were theoretical formulation where I was talking about the background, where is QC, another thing. But how we essentially code or program it is, you can call it primitive, where you would have, I don't know how many of you would have done punch codes, where the computers were very early. It was punch codes where you give the programs, and that is a system where we are in. We are also in that punch code system where it is very primitive. There is no high level system or high level languages for you to write. What essentially you need to write is what essentially you need to build is take a bunch of qubits, let's say we take 3 qubits and add gates, we call them quantum gates. We have X, Z, H, T. It is not direct analogy to our classical computers where we have NAND, AND, NOR, XOR and other gates. There is what we call X, Z, H, Y and T gates. It is a different analogy, different terminology in itself. And this is not the complete list of the gates that we have. So, and before going to that, let us talk about qubit. I haven't mentioned how we can essentially represent qubit. So, as we know, qubit is a vector, right, of 2 components. One is a component with respect to the state 0, and one is a component with respect to state 1. So, we can write it as a vector. We can write this as a vector, a 2 cross 1 vector where we say alpha, beta. So this is a representation or a mathematical representation of qubit. We represent it as alpha, beta. I've written it here. And there's a small condition also, alpha squared plus beta squared should be equal to 1. That is a small condition. So for example, it can be something like point 8, root of 0.8 plus root of 0.4, sorry 0.2. So when we square it and sum it up, it will become 1. So these are the type of numbers that you can essentially put in for a qubit. This is how we represent a qubit. This is how we mathematically represent a qubit, and from this we can build on top of it and find different how we can essentially change the state of qubit, where it can be, and other things. So this is just for 1 qubit, and it will be much more complicated for 2 and 3 qubits. That's why I won't be going to that. So we have, let's say, alpha, beta, and we have written it in a vector formulation, where alpha is associated with the state 0 and beta is associated with state 1. Now, we have gates. For classical computing, we have Boolean algebra, where we act different state on different gates, and we know how it is going to act up. Now, for quantum computing, we have called linear algebra. I think we all know linear algebra. It's simple vector and other vector and matrix multiplication and other things. And we denote a qubit as a vector. And now we have quantum gates to act upon it. We need to act these quantum gates on this. So all these gates are essentially represented as different matrices. All these gates have different matrices, and this is not the complete list of gates. There are actually a lot of them, but these are the main gates that we have: X, Y, Z, another thing. So I've only given. So if you can see here, right, e raised to I pi by 4. This is something called complex numbers. So it is again going to be much more trickier. But let us not concentrate on that. Just take a look at h, x, and z. All these are simple, natural, real numbers. Now, how we compute or how we act a gate on a qubit is simply multiplying the qubit with the gate. So like this. So we have the qubit here, and we multiply the gate with it. That is how we are going to get the result of acting a gate on a qubit. So if you want to find, or if you want to get the result of a gate on a qubit, you essentially need to multiply that qubit with the matrix of the gate. So for example, like if we had in classical bit, we had state 1, and if there is an AND gate, it is going to be, I don't know if there is an AND, let's say NOT gate, it's going to be simple. You're going to get 0. This is how we know how classical bits and gates evolve. Now if we have a qubit 1, 0, this very simple example, 1, 0, that is 1 into state 0 plus 0 into state 1. This is essentially this particular representation. And let us take example of X gate or bit flip or NOT gate, which you can compare and can easily understand. That is 0, 1, 1, 0. And now if we do the mathematics, we do matrix multiplication, what we are going to get is 0, 1. What we are going to get resultant as is 0, 1. If we do the mathematics, we will get 0, 1. And that we can essentially represent as alpha 0 into the state 0 plus 1 into state 1. So essentially we started with state 0 and we got state 1. So this is a simple representation of NOT gate. We don't have AND, OR and other gates. It is not that straightforward. We have gates like Z gate, H gate and others, which are simply different matrices. You need to essentially multiply whatever qubits you have and try to multiply this with that qubit and get the result. Now what if you have multiple number of gates? If you have multiple number of gates, do the same thing. Let's say this is just for X gate. This is for X gate, and add another gate. Let's say we have Z gate. 1, 0, 0 minus Z gate. So just multiply gates after gate after gate. Then you will get a bigger matrix, multiply it with this number, and you will get a final state. So this is essentially how we act multiple gates on a qubit. And this is how we are going to get the result. Yeah, so at least X gate is basically bit flip. If you had 1, it will take you to, if you had 0, it will take you to 1. X gate is essentially doing the bit flip, taking from 0 to 1, that is NOT gate. Essentially similar to that, actually not similar to that, these are different, how will I say? It will be possible, it will be always possible. Yeah, this is 2 by 2. 2 by 2, 2 by 2 and 1 by 2. 2 by 1, sorry. Yeah, so this is 2 by 2, 2 by 2 and 2 by 1. 2 cross 1. So essentially we are multiplying this with 2 cross 1, right? I don't remember. Yeah, 2 cross 1 thing. So you'll get 2 cross 1 as the resultant. I hope I've written it clearly. So you can't directly have an analogy with classical gates. We have AND, OR, NOR. We know what is going to happen, but we can't have that analogy here. Instead of that, we have other type of gates. Because right, in classical we know it is going to be 1 or 0, but in quantum it is not the case. Can it be that superposition, right? So we need different sort of operations to find and to do computation there. I think we need actually a bigger session for teaching quantum gates, so it's going to be much bigger. No, if we know the gates what we are going to apply, we will know if we know the qubits. If we know what qubit. Yeah. Is it flip, is it gate, phase flip? Yeah. So phase flip essentially means the sign changes. So if we had 1 over here, phase flip is essentially the sign. You can say the sign. If it is positive, it will become negative. So the thing over here, the coefficient over here will become negative. So that is phase flip. So Hadamard gate, if you have a what Hadamard gate does is, if you have qubit 1 0, which is just the state 0, it will take that and it will give you a state like this. So Hadamard is this gate. If you do the multiplication with this, so I'm doing that here. This is Hadamard gate, and this is the state 0, just the state 0. That one, the coefficient is 0 for state 1. And what it essentially does is going to do is it will give you 0 and 1. So we have started from 0, just 0, and it will give you 0 and 1. And that too in equal measure, because 1 by root 2, 1 by root 2. If you square it, it will be 1 by 2 plus 1 by 2. So it will be equal mixture of 0 and 1. So that's where we can't directly say how the gate is going to act. So it is going to act in a mathematical way only. Like it will create a mixture of 0 and 1. It might do a phase flip where the coefficient will become negative. It might do other things which we can't even explain with words. It's just mathematical. So that might be a difficult part to comprehend, but if we understand different types of gates, there are only few handful of them which we need to understand, X, Y, Z. And then if we thoroughly do a bit of mathematics behind it, we will get the knack of how to do gates. And now, what if we have multiple qubits? We were talking about just single qubits, was direct forward. Now with multiple qubits, the mathematics will become much more involved. If anybody wants to go look into it, you can look into something called tensor product. And this is the way we define multiple qubits. And then we act similarly using the different gates, and this is how we make a quantum circuit. We have 3 qubits, Q0, Q1, Q2. This is another qubit, and still a qubit, also another qubit called Q4. Now we have different gates. This is Hadamard gate, X gate. This is a 2 qubit gate. In classical also we have 2 qubit gates, where according to the condition of one bit, it will perform the operation the second bit. So it's essentially here, if the state here is 1, it will do a AND operation here. That is 2 qubit gates, according to condition of 1 qubit, it will operate in another qubit. That is 2 qubit. And till this is the quantum circuit. Now, as I told you, we always want to measure the qubits to identify what is a state. And that is what it is happening here. We are measuring each of the qubits. This is the measuring part. And you are mapping or reading it out into classical bits. We are storing that into classical bits, direct forward. And why this is essentially is because we don't have it built a quantum memory. We don't have a quantum memory or a quantum random access memory or quantum RAM. We still need to store whatever that we have found from this circuit in a classical memory or classical RAM. So essentially you can say quantum won't be able to store data, but we will be able to process data. And this is the circuit that we will be building using qubits and quantum gates. Now, we have looked at the mathematics, a little bit mathematics and in a representational way. We can actually do this right now using different Python software development kits available. You can actually code it, but again, the things will be pretty much similar like I've said. You need to add these different gates, different gates to different qubits and build a quantum circuit. This is an example of a Qiskit programming language code, which is based on Python. You can code it right away, you can look at it right away, and there are actually multiple SDKs available to do quantum programming, and most use is IBM Qiskit. It is easy and there are a lot of resources available there to learn. As you can see here, we created a quantum circuit, then we added X gate, this circuit into plus X gate at qubit 0, circuit induce conditional Hadamard gate, that is the 2 qubit Hadamard gate from 1 and 2, and then we measure. So these are essentially the operation that we just discussed, and we can do the same thing in classical Python SDKs, and then connect it to again, I'll probably have it in the next session. Then we can connect it to the backend, or what we call the device that you need to run it to. There are different devices that you can run right now, and you can get the result. So this is essentially a snapshot into quantum computing, how to do computing, various quantum computers, what is the mathematics behind it, how to code and program in it and other things. And I think I'll stop here for some time and take if you have any questions regarding any of the things that I've told. Any questions? So I think probably we can take a minute to grasp all these things. It is of course a lot of things, starting from the fundamentals to some bit of mathematics and again to programming. So if you want me to go over anything again, I can do that also. Anywhere, you still so if you want me to go through any of the sections, I can probably do that also. I hope you understood at least a bit of it. There were a lot of things, of course, and quantum computing is not something that we could be taught in 2-3 hours. But I tried to put that whole lot of things so that we have a starting point where to look forward and where to start reading about it. It's just a starting point. Don't consider it as everything in quantum computing. A lot of things are yet to be learned. So I'll give you a brief understanding of how to probably start reading on that then. So the first starting point should be quantum mechanics. Bit understanding about quantum mechanics is very much needed here, or else it will be very difficult for you to understand the code. So quantum mechanics is essentially the physics where we explain the phenomena in the quantum regime, a lot of phenomena, and essentially once we understand up to quantum entanglement, quantum superposition, and about qubits, then probably quantum teleportation, quantum no-clone theorem, and all these things. There are pretty good books available online, or else you can take courses which are available in NPTEL and others. Also IBM Qiskit, there is a YouTube series on this where they give basics of quantum information. So that's also, I can probably show you that right now if the internet is connected. So this is a platform by IBM, learning.quantum. Sure. I hope all of you are here, so can start second half. So if you have any questions right now, I think the noise question I'll try to answer. Any other questions? Okay. So one of the main problems with quantum computers is the fact that they are very noisy. That is, once you make a qubit, once you produce a qubit, there is a very high chance that the qubit can get corrupted, or so what happened. What I mean by saying corrupted is, you made this simple electron, you made this atom in such a state, and if there is a light shown in, there is some light shown in, or if there is some other disturbance in the environment, that state is going to get collapsed, or what we call become into a simple state rather than a superposition. For example, from 0 to 1, from a superposition of 0 and 1, it will collapse into just 0. One of the states, that is for sure, right? It will of course become one of the states once we measure it. So that is one of the huge problem that we have in quantum computer, and that actually creates a lot of noises. A lot of noise saying, most of the times the qubits won't be in the same state that we require to, and what will happen is the result that we are supposed to get won't be the one that we will be getting from the quantum computer. And this area of research is called quantum error correction. There are different types of error correcting code that is available for us. It is very nascent. It is still being worked out. So one of the error correcting code is called Shor's error correction code, and what it essentially requires is, instead of just having one qubit, they encode the information of one qubit into 9 qubits, so that even if one qubit fails or one qubit get measured and collapse into a particular state, they still have other qubits to make sure that we can still read out, or we can still do the computation meaningfully. So this is how error correction or error is being mitigated in quantum computing scenario, and it is still a very nascent stage. Very recently, so okay, now this error corrected qubit is called logical qubit. So we have, let's say we have qubits, let's say 100 or thousands of qubits, and we call them physical qubits, and once we have error corrected qubit, we call them logical qubit. So it can be the case that you'll have thousands of qubits, you'll have thousands of physical qubits, but 0 logical qubits. That can also be the case if it is not being made that way. So most of the times the current computers are not, quantum computers that is available are not error corrected. They doesn't have this logical qubits architecture. What essentially we have them is normal physical qubits. There will be a lot of errors and a lot of noises. And recently, I think 1 week back only, there was a recent announcement, recent breakthrough by a quantum computing startup, where they were able to bring up 49 logical qubits. It was an experimental demonstration, but it is a very promising breakthrough, because with 49 logical qubits, that is error corrected qubits, it is going to open up a huge amount of computational power. Just 49 is more than enough, and it is going to actually help us a lot. But again, there are a lot of other experimental difficulties there to actually make it useful. Not just the logical qubits is not enough. There needs to be in a particular architecture, we'll have much more practical applications possible. So this is a state, and now to have a very decent quantum computer which can help us do a lot of practical applications, we require a minimum of 1 million qubits. We require a minimum of 1 million qubits. So that is the range that we are looking to attain. I hope this cleared at least a bit of it. Now if you have any other questions, I'll be happy to take. Okay. So I hope there is no further questions. Now we can probably start looking at how to write code or write program in quantum computer. So we'll start with IBM's Qiskit, which is a very popular quantum SDK available for us, and it is more easy to learn. So IBM has 2 main resources for us to start in quantum. One is called IBM Quantum Platform, which you can see here. So if you just search for IBM Quantum, you'll find it first or second search result. Once you go there, you actually would require to make a account. It's very simple. You can use a Google ID or any ID. I used my Gmail ID to create that account. And once we are in, you'll see a platform like this, where you will see different sort of different dashboards where we identify how many circuits or jobs that we run, which we can come to that later. And this is a platform where we'll get overall idea about how much we have used and what we have used. Now there is another interesting platform called Learning, IBM Quantum Learning, which is a wonderful platform. Everybody should definitely check out. This is a platform where you can have bite-sized courses on each of the things that I've just mentioned. To start with basics of quantum information, they have a simple course, 4 lessons. They'll also teach coding, and also they have different video lectures with it, and also some bit of coding alongside with it. So this is a very interesting platform for all of us to check out and start learning at your own pace, and it is very simple to also understand from the things. I hope you all will start looking at this. It's a very simple platform to learn. So here what I'll suggest is, now understand, starting with basics of quantum information, where you can understand qubits in depth and quantum gates in depth. There are multiple quantum gates which I couldn't discuss here, and also mathematics a bit, can brush up the linear algebra mathematics. And then there are other courses, more advanced courses, more advanced quantum algorithms. You can go to fundamentals of quantum algorithms. People are interested in cryptography. Post-quantum cryptography or quantum safe cryptography is a very interesting area where, as I've mentioned before, factorization is going to be broken, and that can't power cryptographic solutions. Now, how will we make cryptographic protocols that are quantum resistant or can't be broken by quantum computer? So there are different types of mathematical problems which can be a base of it, not just factorization. So that is where post-quantum cryptography or quantum safe cryptography comes in. Now there is another thing called variational algorithm design. So this is a bit more advanced, where they discuss about how the quantum algorithms of today are being designed. So it is not that all of the quantum circuits that probably I'll explain in the next section is going to be run on fully quantum. It can't run on fully quantum at this point of time. It will be some bit of quantum and some bit of classical compute. So for example, let's take an example of an optimization problem where the first part will be to create the objective function that we need to optimize. What quantum will essentially do is create that optimization function, quantum function, and then the optimization, the actual optimization will be run by a classical computer. So this is a design that we have right now. So that is where variational algorithm design is also another interesting course that you can start with. So once we come to this IBM quantum platform, quantum.ibm.com, I guess, yeah. Once you create an account, it's a simple process. You need to log in via your Gmail ID or any other ID accounts that we have. You can go here in compute resources and actually find the devices, actually find quantum devices that is available. So as you can see here, these devices, IBM Brisbane, IBM Osaka, IBM Kyoto, and all these devices, right? These are devices either which are really quantum hardware, physical quantum hardware. IBM Brisbane, IBM Osaka, Kyoto are real quantum hardware, that is actual quantum computers which resides in US, and we can access it via our cloud and using this simple platform. And then we have simulator stabilizer, simulator MPS, different type of simulator. So what simulator does is, simulators are classical computers, your GPUs or probably your laptop itself, that tries to mimic the quantum behavior using the mathematics. I've actually shown the mathematics before, right? How quantum max works out. You have vectors, you have gates, that's basically matrices, and they try to actually do this mathematics and find the results for you, and that is simulator. And right now we are at a place where simulators gives you the right amount of right answer, because even the classical computer can actually simulate up to 20-25 qubits. They can simulate up to 20-25 qubits efficiently, but beyond that they'll crash. Beyond that they won't be able to do it. And in your local system, that is your laptop, if you have higher CPU, probably you can simulate up to 10 qubits. You won't be able to go beyond that. So this quantum systems that IBM provides, it's just about IBM. It is one of the companies that provides quantum systems. There are multiple companies that provide quantum systems, not just as IBM, AWS, Microsoft. There are hundreds of quantum startups actually. And so this is the overview of computer resources. Now to the actual coding. So here you can see a quantum composer, IBM quantum composer. So that's a very interesting place where you can go and play around. IBM quantum composer. So what it essentially does is, it helps you build quantum circuits visually. So you don't want to code, which actually helps you a lot. So this should be your starting point. Very interesting platform where you can simply use different gates. You can play around with it. So here I've added a Hadamard gate, it's an H gate. Then I have added a measurement. So now if I add another gate over here, so it already writes the code for me here. This is a Qiskit code that's already there. This is the Qiskit code. They write the code for you there, and they also show you the probabilities. They also show you the result of it, result after you measure it. So it's a very simple place for you to actually start playing around in quantum. So you can also add different multiple qubits. You can add how many ever qubits you want, and you can add multiple gates. So before adding all these gates, I think it's important to understand these gates in a mathematical way. So once you do the courses, you'll be able to understand it. I'll put so if you can see, okay, there is so okay. So if you can see, we have probably now you can see here, right? I've mentioned before, Hadamard, what Hadamard does is takes a qubit, and also one thing, all the initial qubits are in zero state. All the initial qubits are in zero states. That is a state that will be. So that will be this state. It will be 1 here and it will be 0 there. And if you do a Hadamard operation, if you add a gate, Hadamard gate, what you will get is equal distribution of zeros, 0 and 1. Equal distribution of 0 and 1. So here you can play around and actually understand the operations or process of different gates that you have. So now let us have a gate called Y and delete this gate. So you can see what happens. Once you add gate A, gate Y, the probability of 1 goes high. Again, similar phenomenon. So this is where you can play around qubits, play around gates, and also understand and also get the quantum Qiskit code for it. So you can add multiple qubits, you can add multiple gates. So these are essentially what we call 2-qubit gates. I'll add them and show you. These are essentially 2-qubit gates. Where you can do a conditional process or conditional operation according to the state of this qubit. So once you have a basic understanding about each gate and what it does, to understand, okay, this gate once applied to this particular qubit will give me this. This gate applied to this gate, this qubit will give me this. Essentially, we need to understand how each of the gate process on 0 and 1. 0 state and 1 state. If we can understand most of this thing, then this will be a very interesting platform to start your quantum learning. And you can also get the code here. And if you can see, there is something called Q-sphere. I'll show. So there is something called Q-sphere, which is essentially a representation or visualization of that qubit. So so this was essentially 0 initially, and this is NOT gate. It will be 1 afterwards, right? 1 afterwards. So 0 is here, north pole, 1 is in the south pole, and this infinite possibilities in that sphere is all other states that you have. It's going to be infinite possibilities in that sphere. That is going to be all the possibilities that you have and that you can work with. So imagine that sphere. All the points can be a state. All the points can be a state and can be a mixture of 0 and 1 and can represent as 0 and 1. So if we can play around with it, we can actually see how this is going to change. So if you have Hadamard gate, you can see there is some part in 1 and some part in 0. So this is how the mixture comes in. If you have, let's say, Z gate. So what happens with Z gate is nothing is changing. The mixture is not changing, but the phase, as I said, is going to change. Right? The red became blue. So that actually, if you go through the max, you'll be able to understand. So what is phase? Another thing. It is actually a bit difficult to make you understand phase without going to max. So I hope this representation will give you a bit idea. So once you have played around with this, you can start to look at writing code in lab or in Jupyter notebook that we have over here. So you can go to here called lab. So this is a Jupyter notebook in itself. It is just a Jupyter notebook, nothing different, but inside the IBM quantum environment, so that you can easily interact with all the quantum systems that IBM has, because it will be easy for us to do it here. So once you start, usually this will be the launcher, and I've already have some code here, that's why I have all these things, but for you it will be this particular launcher button, and you can start with Python 3 kernel, that is Qiskit kernel. So what it does is, once you have that Qiskit Python kernel, it automatically imports all the necessary libraries you need. So that makes it easier. It automatically start with all the necessary Python libraries that you need for Qiskit. Or else you can start with, again you can start with just the Python 3 kernel. If you want that, that's also possible. If you want to have other libraries, that's also possible. You can start with another Python kernel. Or you can start with this quantum kernel of Qiskit, which will essentially automatically load all the libraries. So in the quantum composer program, we haven't gone through the architecture, the code architecture structure, but here I'll try to explain it. So this will also be in a surface level, because myself is not a quantum programmer, I'm more on the theoretical side of it. So essentially what we need to build any quantum algorithm is a circuit. All the quantum algorithms is essentially just circuits. They are just circuits, and to build a circuit, what you need is quantum qubits or quantum bits. And now to read out the measurements, you need classical bits, because without that we won't understand what is going on there. And that is where you import quantum circuit, that is a function where we can build circuit, and then you import quantum register and classical register. They are the functions where you can actually define qubits and classical bits. I'll explain how we can define that later. And transpile, assemble, AER and execute, they are functions which will help us to run the circuit. Basically execute means executing the circuit, not running the circuit. Transpile is another step before that to actually convert that circuit into different form, which you don't need to understand right now. And AER is a bigger function that we have, bigger library that we have, which hosts a lot of simulators, the devices that we can run on, because devices that we can run on which are classical, they're not quantum, they're not actual quantum, which are classical. Now we have IBM Q, which is just the IBM Q thing, and job monitor, which is another interesting function where we can, so once you start the run, right, once you start the execution, you need to understand how, where it is going, is it started. So why we need job monitor is because all these systems are in cloud, right? So once you submit the job or once you submit the circuit to the cloud, it might be in queue, because there will be a lot of circuits being piled up to run. So it will tell you if it is in queue or if it is run or if it is run successfully. And then we have visualization, which will help you to visualize in multiple different formats, which I'll let you know later onwards. So this is where we define registers. Initial part, quantum register, classical register. So that is Q, we make a quantum register Q with 2 qubits. Quantum register with 2 qubits. So if you need 3 qubits, quantum register 3. And if you have 2, definitely classical register should be 3. Sorry, classical register should be 2. Similar to the number of quantum register, you should have number of classical bits, because then you need to read out all the information. I think I've run this here. So this is where I can probably show in composer here in side by side. So we have 2 qubits. We have added 2 qubits, that is how, and essentially it will have 2 classical registers, so it's automatic in the composer. That is what we have done in the initial thing. Now next thing that we need to do in Qiskit is to define the circuit. So circuit is essentially, for circuit you need to have classical and quantum bits, or we call them registers. So that is what I have done here. Circuit equal to quantum circuit QC. Quantum register. Zoom in. I don't. Okay. Fine now. So you need to define the circuit. You can define the circuit equal to quantum circuit. That is the circuit builder. And you should have classical register or a quantum register. So you can also just define it like this. You could also just define it like quantum circuit 2. That means number of qubits 2. You don't need to actually write Q and C, but just to start with, that's why I've written Q and C. If you just write quantum circuit 2, that means 2 qubits, 2 classical bits. It's already understood. So it is direct forward. Now, this is circuit that we have defined. So we usually write QC for quantum circuit. QC equal to quantum circuit, which is the normal notation. Then we have circuit. Now this is where we add qubits. This is where we add qubits. Sorry, not my bad. Add gates. This is where we add gates. We define circuit, we define qubits. Now we need to add gates. So this is where we add gates. There is a circuit dot H. For all of the gates possible, if you can see here, these are their function names. For example, Hadamard is H, Z is Z, and other things, but you can find it here also. So if you add Hadamard, you can find this is H. If you add, let's say, NOT gate, you can find X. So you can find the actual notation or the name of that gate that you need to define it using this one, or you'll have it in the content documentation itself. Once you study the learning courses that I've shown you, you'll be able to identify which gate and which name. It's very simple to find that. And first we have added H. So let us add H over here. See, we added H. So we have added H. Now the second gate that we added here is control node. That is a controlled operation. Okay, before that, so how we defined here is H on Q of 0. That is the quantum register, 0th quantum register. As we know, the numbering starts from 0, 0, 1, 2. It's not 1, so numbering starts from 1. So if there is 2 qubits, it is 0, 1. So Q of 0 is the first qubit here. Second qubit 1. So Q of 0, but essentially you can also, if you define it like this, quantum circuit 2 without having Q and C, you can simply write, I am taking QC as my quantum circuit, QC H dot H 0. Direct forward, just 0 matlab 0th qubit or the first qubit. And this is how we define where to act the gate on. Now the second gate is a 2 qubit gate, which is called controlled X, where controlled X, where there is action of 2 qubits. So I'll explain this one to give a understanding. So this gate, that is NOT gate, will only act upon this qubit if the state here is 1. If the state here is 1, then only this controlled NOT gate will act on the second qubit. If it is 0, it won't act, it will stay as it is. So if it is 1, it will do NOT operation in this qubit. NOT is just bit flip. it goes from 1 to 0. If it is 0, it is 1. If it is 1, it goes to 0. And that is what is control node. Now we have multiple control gates. If we can see here, not just one, we have okay, it's not showing here, but we can have controlled Z, controlled X, all those single qubits. We can have a controlled version of that and 2 qubits for the 2 qubits. So let us add that control node operation here. So this is the control node operation. This will become the controlled node operation, and this is a circuit that we have essentially built. A simple circuit with one single qubit gate and one double qubit gate. Simple circuit that we have built. And here to define it, first we should have the control gate and the second gateway which act upon it. Control gate and control qubit and the second qubit where it is acting upon. So this is essentially the way we need to arrange it. As you can see here, the control gate is here. Control is 0 and the qubit which is acting upon is 1. Now the next step is to measure. Next step is to measure the result, and that is circuit dot measure. It can be direct forward, just write circuit dot measure. QC, that is, we can define Q should be go to C, classical register. And to draw the circuit, you can use a function called circuit.draw, and this MPL, if you just write circuit.draw, it will actually give you like a staggered lines circuit which won't look good. So but this function, this MPL function will give you a graph like this. Okay, probably need to start it, but a circuit like this. MPL will give you a circuit like this. If you just add circuit.draw, it will be like a staggered line where it will be like this. It won't look good. That's why use MPL. So once you draw it to identify you have got the exact circuit that you wished, then you can go on and identify the device that you need to run on. So as I have shown you before, I will show you again. Okay. There are multiple devices that you can run it on. There are multiple devices, so you can see IBM Brisbane, IBM Osaka, IBM Kyoto. All these are real quantum hardware, real quantum computers with 127 qubits, 127 qubits, 127 qubits. These are other measures that you sees how fast this is. Fast these computers are. Now these computers, these premium computers which have 100 plus qubits, they are premium. You need to actually pay for it to run it on. We get a 10 minutes free run each and every month. So you can also use that for free computing. But to run it on this premium version, you need to actually have much more evolved coding in Qiskit, because you can only access it via other libraries called IBM Q runtime, which is much more complicated, so I won't be going there. So we'll simply look at the simulator here. All the simulators that we have, simple, but to run in the real hardware, you might need to require something called IBM runtime, which is another programming level. So this simulator, we can use, the most famous and most useful one is state vector simulator over here, that we have used multiple times and have found it to be very useful. And we can also use quantum simulator, IBM को quantum simulator again. So if you can see here, simulator / state vector matlab, it is using the state vector formulations or mathematics behind state vectors to simulate it. MPS is called matrix product state. That's another mathematics where we can simulate it. All these are essentially different types of simulations. So this will give you a different result than this. That is why there are different simulators available, different classical simulators available. And we rarely use this 5000 qubit simulator, which is actually not really useful. Most of the time will give really poor results. We mostly use quantum and state vector. They give really good results. And this is how you define. So we use by a function called AER to get this backend. We call them backend. AER dot get backend. First one we have defined state vector simulator, one of the simulator. Second one quantum simulator. There are two simulators I have just defined. You can call many other simulators. Now here is where the execute comes in. Execute part. So can it? Yeah, this is overall. Yes, this is overall. So only the second simulator will be used, just to define it. That's why. So job equal to execute. Then you define which circuit you need to execute. That is, we have defined circuit here, the name of the circuit, and then which backend you need to execute, which is the device that you need to execute. I've just given simulator with two options. I can hash it out once I want to use another one. Then shorts. This is where you can define, as I've mentioned before, the probabilities you can only see if you measure multiple times. That's initially itself I was told, right? If you measure it 1000 times, only that show that uncertainty. So to that, how many times the system need to measure? That is what you call shorts. We usually give 1024, or you can give anything. It doesn't matter. But if you give one, it is actually not going to be helpful, because it's just like classical. You've just measured once and there is no quantum phenomenon that is going to come out. So it at least have 1000, minimum 1000 or more than 1000. That is pretty much required. So this is very required. This is where we give a shorts, or number of times you need to run the circuit and actually get the probability for. And then once you have executed, you can call it as a job. And this is where job monitor comes in help, because once you are submitting to a cloud, it is going to have a queue. Usually it have queue. So if I can show you here. So these are the jobs that I've sent. These are jobs that I've sent, status completed, created, completed, the compute resource that I've used. So this is where we can also see how my device is being performing. So once we had access to a premium quantum computer from IBM with 27 qubits, real hardware. It was IBM Mumbai. I can show you probably here. Yeah, IBM Mumbai. So we had access to IBM Mumbai, 27 qubit premium quantum hardware. You need to pay around some crores to actually get access to this. So for this one, you can see how many jobs are pending. Like 2 jobs are pending. It is online, and it is going to take a lot of time to run any program on this. And that's where this dashboard comes in handy, where you can see the status, where it is being. So if we're just using a simulator, you probably won't need the help of this dashboard, because most of the time it will complete within few minutes. Won't go beyond some minutes. If it is a bigger quantum machine learning algorithm, it will take some time, or else it will just be finished within some very few time. So now, once the job is run, you need to collect the result, that is job.result, and then you need to have this thing called get.counts. So once we have the result, this is probably a dictionary where you have multiple values stored, and counts are essentially defines how many number of times we got 0 and how many number of times we got 1. So you can see here, counts, you can see 0, 0 I got 4,102 times. 1, 1 I got 4,090 times. So this is essentially getting the counts for each of the states. So don't get confused over here. So I will regress a bit and try to say what does it mean by 0, 0 or 1, 1. Now, because essentially we were all looking at just one single quantum state or qubit, which is either 0 or 1. Now, if we have 2 qubits, there can be 4 possibilities: 0, 0, 1, 0, 0, 1 and 1, 1. And each of these possibilities will have different probabilities associated with it according to the computation we do. And now here, according to the computation we do, we got 0, 0 4,000 times and 1, 1 also 4,000 times roughly. So that means they are with equal probabilities, not exactly equal but equal probabilities. And to get the histogram, to visualize it in a much better way, this is where you can visualize it. Plot out histogram and see for yourself that this histogram was what was that we got it here also, that we got here also in the composer. Yeah. So that is possible. So if you can see here, we have 0, 0 and 1, 1, no other probabilities in other states. If you want to play around, you can also add probably U, and it completely shifted. So to have Hadamard over here, yeah. So now you got probabilities for all of the states. You got probabilities for all of the states. So, and you have the code over, you can directly import to Qiskit and run it. So this is the basic starting point, and this is where we can write all the algorithms. All algorithms are nothing but a quantum circuit. Advanced algorithms there will be a quantum circuit plus a classical part. Classical part, I think you will be much more easier to able to handle. So this is essentially the starting point of quantum programming, and this is how we can start with the composer and then go to IBM Q Lab, where you'll have all the things you require to start running. So I hope this was a good starting point for you to go on and try it out yourself. Definitely try the composer. It's very intriguing to find out different gates, what it does and other things. So if you have any doubts, yeah, please ask. So any other thing I need to explain more in probably quantum computing or in the quantum programming part, I'll be happy to answer. Can it be? Simulators. Yeah, I'll show you again. So here you can see all simulators. There are actually 5 simulators available.
These 5 simulators are
Yeah. So we can use any of it. It's completely up to you. each will give different answers, but mostly similar, slightly different here and there. As you can see, 32 is the biggest number that we can accurately simulate with classical resources. Beyond that, I mean, not even 32, we haven't even attempted to simulate 32. It's much more difficult to simulate. It will take a lot of time. You can play around and just add, let's say, 20 qubits and just add only Hadamard gate to each of these qubits and try to see how much time it is going to take. It's actually going to take a lot of time to just do this. And you have other systems. Usually, before 6 months actually, we had free systems, free IBM systems with qubits up to 7 qubits, just 7 qubits, which was much more compact and could have been easily run. Just like your simulator, we could have run 5 qubit operations on it, but IBM have completely scraped it. They have completely removed it. As you can see, it starts from 27 right now. Minimum is 27, and it's because 5 qubits can be easily simulated in a classical computer. So we don't need a 5 qubit quantum computer. If it can be easily simulated in a classical computer, then there is no need of a quantum computer where it is 5 qubits. So that's where 27 is the minimum that they start, because after that it will be much more difficult to do it in quantum computer. So now here I think you still have 10 minutes. You still have 10 minutes for running all these high-end qubits, all these qubits, just 10 minutes. That is actually probably won't even get you one circuit run. The plans are a bit on a higher end. So yeah, we can start with simulators initially. Afternoon session, I'm planning to take QML, right?
Our comprehensive overview on techniques, taxonomy, applications and research directions of deep learning, and the other one is deep learning in computational medicine. So what we have to submit by the end of this article discussion is, so what are the key principles and practices from the article which we are going through. So that is one part. And at the same time, application of principles or practices. So that should be submitted individually. Key principles or practices should be submitted as a team. And key takeaways from the article also can be submitted as a team. So, so I gave you in the WhatsApp group regarding what should be submitted. So in that, please check it once with 3 to 4 lines of write-up, bridging theory with practice. So this is what we have to for this journal articles. Similarly, we also need to have this FDP reflective journal. So all the participants who are registered in the ATAL FDP portal, all of them should submit these, which are mandatory. Okay. So one more is FDP reflective journal, which is also to be submitted by the participants, and which is a 2-page, which is a 1-page reflective journal. So that reflective journal is all about the whole week. So complete whole week meda vachina reflection anta kuda you have to submit in that is again instructions are given for that too. So that is identify 3 key learnings or outcomes from the FDP, key 3 key lessons that you will implement, that is in future what you're going to implement, and share an implementation plan for your 3 key lessons. So whatever you could do as an outcome of this FDP, that you have to submit as a 1-page reflective journal. So this is one document which you have to submit, and the other document is about these two. Article discussion lo meer cheskunna article discussion lo outcomes evaithe unnayo, after the learning whatever you have acquired from this discussion, that has to be submitted as the 2-page summary. So 2 documents to be uploaded in the portal. Whichever is comfortable to you. Better it is if you have, when we sit in the lab, systems will be provided to you. So if there is something which you could type it there itself, you could prepare and you could submit. Just నాకు మెయిల్ చేసినా సరిపోతుంది అవి. Okay, that is what I'm telling. If whatever is comfortable to you, you can do that. If you submit me as a handwritten, again I'll try to make it as a typed material, or I'll just try to scan it. I'll just contact the coordinator. If at all it is accepted in any way, that's fine. Okay. Thank you.